Have you ever stopped to look at your glasses or the screen you're watching this on? What about a simple drill bit in a toolbox? They seem pretty ordinary, right? But they're hiding a secret, an invisible, atom-thin coating that gives them some pretty incredible superpowers. Today, we're going to dive into the amazing science that makes our world tougher, more efficient, and way more durable.
So let's just start with this question. How do you take a normal piece of glass and make it basically scratch-proof? Or how do you take a standard tool and make it unbelievably tough? How do you add these amazing properties without making the object any bigger or heavier? Well, the answer lies in the incredible science of thin films. This is a process where we can build brand new surfaces, and I mean literally one atom at a time. We can give materials properties they never ever had before. It really sounds like something out of science fiction, but it's happening all around us every single day. At the heart of all of this is a process called vapor deposition. Now, the easiest way to think about it is like atomic spray painting. Seriously, inside a vacuum chamber, you take a solid material, turn it into a vapor, and that vapor travels and condenses onto a target object. That's what we call the substrate, and it forms this perfectly even, incredibly thin new layer. And what's really amazing here is just how versatile this is. I mean, this isn't just about making things tougher. By picking and choosing different materials to vaporize, you can precisely control a surface's properties. You can change its electrical conductivity, how it handles heat. You can make a lens anti-reflective, or even make a piece of metal completely rust-proof. The possibilities are huge. So how exactly is this atomic spray painting done? Well, it pretty much boils down to two major methods. You can think of them as two different flavors of vapor deposition. They get to a similar result, but the way they go about it is completely different. Let's break them down. Okay, first up is Physical Vapor Deposition, or PVD for short. So if vapor deposition in general is like atomic spray painting, then PVD is kind of like a microscopic, hyper-precise sandblasting process. Except instead of eroding a surface, it's actually building one up. So here's how it works. Inside that vacuum, you take your coating material, let's say it's titanium, and you physically knock atoms loose. You can do this with intense heat or by just blasting it with ions. Those freed atoms then fly in a straight line until, bam, they hit the target, sticking to it and building up that new layer. And that straight line is the key thing to remember here. It's what we call a line of sight process. The vapor literally has to see the surface it's going to coat. And just how thin is this layer we're building? We're talking 2 to 5 microns. Now, to put that into perspective, a single human hair is about 70 microns thick. So yeah, this technology allows for an absolutely astonishing level of precision, creating these powerful coatings that are practically invisible. So the bottom line for PVD is this. It's fantastic for creating incredibly hard, wear-resistant coatings with super precise control. That makes it perfect for things with relatively simple surfaces, like tools or camera lenses. But that total reliance on line of sight means it has a really tough time coating the insides of complex, twisting shapes. All right, let's move on to our second method, Chemical Vapor Deposition, or CVD. If PVD is our atomic sandblaster, you should think of CVD as baking a microscopic layer cake. It uses reactive gases in a totally different way to get the job done. See, with CVD, you don't start with a solid material at all. Instead, you pump specific gases into a heated chamber. That intense heat then triggers a chemical reaction which causes the gases to decompose and form a brand new solid material that deposits itself evenly on every single exposed surface inside the chamber. It doesn't matter how complex the shape is. And when we say intense heat, we mean it. For these chemical reactions to actually happen, you need temperatures ranging from 600 all the way up to over 1100 degrees Celsius. That's hotter than many blast furnaces. This massive amount of energy is what drives the creation of these super high-purity coatings. And that, right there, brings us to the core trade-off with CVD. Its huge advantage is creating a perfectly uniform coating on even the most complex shapes you can imagine. Think about the tiny, intricate pathways inside a microchip. The downside? Well, it requires that extreme heat, and it involves handling some pretty hazardous chemicals, so safety is a big deal. Okay, so we've got two really powerful techniques. One is physical, one is chemical. One is a direct line-of-sight deposit, and the other is an all-encompassing chemical reaction that coats everything. So how do engineers choose which one to use? Let's put them head-to-head. When you put them side by side like this, the choice becomes a lot clearer. PVD runs much, much cooler, so it's safe for a wider range of materials that just can't handle that extreme heat. But when it comes to uniformity, CVD is the undisputed champ. That chemical reaction gets into every single nook and cranny. And that's exactly why you see PVD used for things like giving aerospace parts extreme heat resistance or making cutting tools incredibly hard. Meanwhile, CVD is the absolute king of electronics, and its ability to create these super pure, uniform layers makes it perfect for things like biocompatible medical implants.
Okay, so we've gone pretty deep into the technical weeds here. Let's zoom back out for a minute and really look at the massive impact this invisible technology has on the world we live in every single day. This breakdown is just fascinating. Look at that. Over a third of all these coatings are used in electronics. We're talking about the silicon wafers that become the brains of your phone, your computer, everything. But you also see these huge chunks going to make industrial tools last way longer, making jet engine parts more resilient, and creating those biocompatible coatings for medical devices. And that is the big takeaway here. This isn't some niche, futuristic lab experiment. This technology is the unsung hero behind so much of our modern world. It is the reason our tech can be smaller, faster, and stronger than it has ever been before. Ultimately, it all comes down to this. The ability to manipulate materials at the atomic level is one of the absolute cornerstones of modern engineering. Knowing whether to use a physical process or a chemical one to enhance a material, that's a fundamental skill that's driving innovation forward. And that leaves us with a final thought. We are constantly discovering new materials, and with them, new challenges. As this technology gets even more advanced, more precise, and more efficient, what's the next frontier? What incredible properties are we going to be able to build into the surfaces of the future? Thanks for joining me.